Chip?
So we had few people who wanted to attend but could not because of the time conflict. So today's talk we are having Asian theories and talk about his work on interference management. And
okay, so yeah, so this is mostly adapted from my qualified slides. Ooh la la. So, but I hopefully I can give a brief overview of my work on cooperative interference management in wireless networks. So I guess where you see a lot of slides.
Okay.
Yes.
You're going to talk about the same old thing?
No, I have some.
Don't. Okay. Don't be teased.
Okay, so this is the motivation. So in the wireless networks, this is an envision of the future of wireless networks, and we envision that there's a heterogeneous structure, and the demand to high-speed ubiquitous broadband access has been growing, and to achieve this goal, however, we have two major issues. One is fading, and the other one is interference. Okay, and so for fading, we have for the last decade we have a lot of research on this, and we propose schemes like MIMO opt-ins and commutations to alleviate fading intracell. So we successfully increase the point or intracell throughput. And nowadays, the bottleneck seems to be the interference among different cells. And in this talk, I want to propose cooperation, and I want to see that explore the opportunities for novel techniques for interference management using cooperation. And you can see from this picture that cooperation can happen among, for example, among base stations. And I'll motivate that why cooperation can help with interference in the next slides.
We're talking about the up or the down or both things?
In general.
Okay.
So the goal is to break the interference barrier in the wireless networks. So why cooperation can help, I want to give this very simple toy example to give you guys some ideas. So imagine that one person in BWRC wants to convey X1 to the other person also in BWRC. And assume that the channel is very simple, there's no noise, and the channel gain is +1. So, of course, this receiver can get as 1. On the other hand, if there's another pair of transmissions happening, say in wireless combinations, then because they're far away and assume the same channel, because they're far away, so they don't have interference to each other. And of course, receiver 2 can get X2 as well. However, if these two transmissions happen in the same room, for example in this room, then they will cause interference. And let's say the interfering links have these channel gains. Then receiver 1 gets X1 minus X2, and receiver 2 gets X2 plus X1. And they cannot recover their desired signals, X1 and X2. Okay, so we see that interference is bad. And to avoid interference, the state of the art is to orthogonalize these transmissions. For example, I can turn off one transmission, I can turn off one transmission at one time, and then I can achieve two symbols using two time slots, for example. Okay. So now I want to achieve, say, for example, two symbols in single time slots. And I can do that using cooperation among these two receivers. For example, I can send the received signals at receiver 2 to receiver 1. And then receiver 1 has two linear equations, x1 minus x2 and x2 plus x1. So I can get x1. Similarly, I can send, if I allow cooperation from receiver 1 to receiver 2, I can send x1 minus x2 to receiver 2. And then I can get x2.
This is via some alternate channel.
Yes, for example, they have a backhaul Ethernet connection. Then you can transmit this signals. This is just a for example.
The orange ready guys would be the mobile terminals, and the others are connected to the backbone. So they have some broadband link
or something like that.
Some broadband link to communicate with each other.
So So in this very simple toy example, you can see that cooperating can help. But the question is, does this happen in reality? So, and these opportunities does happen in even current systems. For example, in the wireless ad-hoc networks, say that we have two pairs of transmissions, and notice that if they are close to each other, then they will cause interference to each other because they are in the same air. But note that these nodes are not isolated because these transmitters and these receivers that can overhear each other's transmission or reception. So you can have collision among these terminals induced by the air. So there are opportunities in the, for example, in the wireless networks. And even in serial networks, we have these opportunities because these base stations are connected through infrastructure backhaul networks. And even in the current systems, we have some operation in the current system, like the soft handle of the CDMA systems. Okay, so this is kind of a motivation of that. And my work, so my work is focusing on how, because of the physical constraints, so the amount of cooperation among these terminals is actually limited in the real world. So I want to find out what's essentially how much interference can this limited cooperation have to mitigate. Okay, and here's the numerical examples that I have for my results, primary results. So in this example, let's assume that the mobile to base stations is 20 dB, SNR is 20 dB, and I'm plotting the user data rate versus the INR. INR is the interference to noise ratio in the crosstalk. Okay, and I'm plotting in this example the cooperative rate is 2 bits per second per hertz, and the rate is the unit is per second per hertz. So the black one is the baseline where if we use orthogonalization among these two transmissions. For example, I use TDMA, I use frequency division like this, for example. Then I can achieve only half the rate when half of the capacity when there's no interference. So the dashed line, the red dashed line is interference-free capacity. And now without cooperation, the optimal, the best achieved rate so far is characterized by Atkin Shen Wang in 07, and that is the red solid line. And this is the information theoretic capacity, and that is within 1 bit reversely to the information theoretic upper bound. So it's optimal in highest number of cubes. And now the blue dashed line is the upper bound when I allow these two base stations to cooperate in an unlimited fashion. So basically, I have a cycle system because I assume that these two base stations they can cooperate in an unlimited fashion, so they can exchange information in arbitrary way, and that gives the upper bound of the blue dashed line.
So you can achieve above the
Difference capacity because you can use these two receive antennas.
if they code together.
Yes. I can do joint code.
Joint.
Yes, and I can have a beacon from that. Yes.
To research.
Yes.
Tails up as the INR goes up.
Yes, because now I have a stronger channel from the other because for user one, right, you have a stronger path from the transmitter to the second base stations. The second stations can have this stronger signal and convey this stronger signal perfectly to the first base station. And then they can decode jointly, and then you can have a view from there.
What is in here is not really power control. It doesn't have, because what happens on the right hand side, why does the blue curve go up? It's actually the transmitted power